Hi everyone. Addressing your feedback questions from today's lecture on colligative properties, boiling point elevation and freezing point depression. Those are both colligative properties. Could you explain why does the pure water have a higher vapor pressure than the sodium chloride water mixture in that first example? You said something about less substance on the surface. What did you mean by that? So this is sort of a qualitative explanation of freezing point or boiling point elevation and vapor pressure lowering. So we think of vapor pressure as occurring due to this spontaneous evaporation of solvent particles or any liquid particles spontaneously evaporating and going from the liquid phase into the gaseous phase. And again, you build up a vapor pressure if you encapsulate, if you cap this system, eventually it reaches equilibrium and you have a constant pressure of evaporated particles that's characteristic of the liquid and of the temperature that it's at. But if you have solute particles dissolved in your solution, so you assume that they've replaced some of the original solvent particles, then I think about this at like what's happening at the surface. And what's happening at the surface is that you have solvent particles evaporating. We'll assume they are the volatile ones. If they're evaporating and you have solute particles dissolved in, well, the solute particles, if they're non-volatile solutes like sodium chloride, sugar, anything that doesn't have an appreciable vapor pressure, that doesn't evaporate spontaneously, well, they are not going to go into the vapor phase. And as a result, on average, you'll have fewer solvent particles evaporating simply because there are fewer of them on average at the surface. Again, that's just due solely to the fact that the solute particles are there and taking up some of the spots at the surface as well as throughout the rest of the solution. So I prefer that interpretation, just that the solute particles are there taking up space, preventing the random motions, restricting the motions of the solvent particles, because it doesn't matter what these particles are, these solute particles are. They could be anything and they'd still be taking up the same fraction of space on average. And now I should clarify, I didn't make this point. Colligative properties, that argument that it doesn't depend upon the identity of the solute, that's true, but it's mostly true for dilute solutions. If you make very concentrated solutions, then the approximation that it doesn't depend on the identity of the solute, that does actually fall away. That does eventually fail. But for the most part, it doesn't matter what the solute particles are. If it's a dilute solution, they're just taking up some of the evaporation spots, if you like. Why does more solutes lower the freezing point? So again, they're sort of the same thing. The idea is they're there, the solute particles take up space and they prevent the solvents from crystallizing into a solid. In order to make something crystallize, you need to cool it down, pull out a lot of energy to cause it to spontaneously order. If you were to pump, think about this the other way. If you were to if you had a crystal solid, if you had a solid mixture, if you wanted to cause it to become a liquid, if you wanted to melt it, that's going into an increase in disorder. You would drive that by raising the temperature. But if the solution is already, if that solution is already fairly disordered, then that accelerates the push to disorder, and you don't need to heat it up as much to melt it, meaning that the melting point should be a little bit lower. And we think of melting and freezing as being the same process, just in reverse. So in both cases, you can think about it in terms of order and structure, and the fact that the solute particles add to disorder. They disrupt the formation of order in a crystalline solid, and as a result, you need to cool it down more. You need to lower the temperature even further to favor order, because the solute particles spontaneously, they necessarily increase the amount of disorder. What difference does the Van't Hoff factor make? I'm still confused by the Van't Hoff factor. All right, so the Van't Hoff factor is something we add on to our simple boiling point and freezing point change equations. So there were two of them. We said that the boiling point elevation should be dependent on the concentration of the solutes, the total concentration of the solutes, and the freezing point constant. And there's a boiling point constant. And there's a similar one for freezing as there is for boiling. So usually if you look at a bottle and the bottle has a particular concentration on it. So if I say I have a 0.1 molar solution of sodium chloride, well, we understand at this point that sodium chloride is an ionic substance, and ionic substances, when they dissociate in solution, when they dissolve in solution, actually separate into separate ions. So you don't have just sodium chloride as a molecule. We frequently like to think about molecules, but this is molecules being tiny little bundles of atoms, like water is a tiny bundle of atoms. Sodium chloride is not a molecular compound. It's an ionic compound. It actually exists as separate, positively and negatively charged ions. Those ions are attracted to each other, and that's what keeps them together, because they're oppositely charged. That's what keeps them together as a compound. But when you dissolve them in solution, they actually tend to separate into individual ions. So for every mole of sodium chloride, the solid, you get 1 mole of sodium ions and 1 mole of chloride ions. Each of those is a solute, is a separate solute. So your total concentration of solutes ends up being twice what you might have expected if you're just looking at the label on the bottle that says 0.1 molar sodium chloride. Its total concentration of solutes is 0.2 molar solutes. 0.1 moles per liter of sodium ions and 0.1 moles per liter of chloride ions. 0.1 molar sodium chloride, but individually you have 0.1 molar sodium ions and 0.1 molar chloride ions. So together their total concentration of total solutes is 0.2 molar. So to either add to confusion or to clarify confusion, we introduce this Van't Hoff factor. And the Van't Hoff factor takes into account the fact that a lot of substances break apart when you dissolve them in solution. They don't stay as whole individual particles. They separate into constituent particles. So yeah, the Van't Hoff factor basically gives you a measure of how much they dissociate. Do they dissociate into 2 parts, into 3 parts? If they dissociate into 3 parts, then the effective concentration of solutes is going to be 3 times higher than what you might perceive, or you might predict. More particles for magnesium chloride shouldn't... this is a question about the last clicker question I had. You said that there should be more particles for magnesium chloride. Shouldn't that have led to a decrease in vapor pressure? Why was that the highest? You're correct. Magnesium chloride does have the highest Van't Hoff factor of all of those solutes. It dissociates into 3 particles, 1 magnesium ion and 2 chloride ions. So it dissolves into 3 parts instead of just 2, like lithium chloride and sodium chloride do. And yeah, that actually does make the vapor pressure decrease more. So it should have the lowest vapor pressure. But the question was actually about which one has the highest boiling point. And the lower your vapor pressure, the higher your boiling point. So that one does have, that solution did have the lowest vapor pressure, and subsequently it has the highest boiling point. I was confused about quiz answers. I'll be posting the solutions to the quiz answers very soon. I have a couple people who may need to make it up, but I'll be posting those soon, and I'll be happy to discuss them at any time. How can I study for quizzes? Going through the homework, checking through practice problems posted in the suggested practice problems in the book. Those are listed on the course website. Coming and talking to me, checking Khan Academy. They have lots of resources. But generally, I would say look to the homework as a little bit of a guidance. And if you'd like to see some of the types of questions I've been known to ask, you can check my previous exams, which are posted also on the Brightspace website. How do you know when the boiling point or freezing point changes? Now, I wasn't entirely certain about how to interpret this question. Do you mean under what parameters will the boiling point and freezing point change? Boiling point will change. So they'll both change if you have a solution instead of a pure liquid or a pure solid, for that matter. Boiling points always increase, freezing points always decrease as you introduce solutes. So that's one way you can automatically know that the boiling point of a liquid will change. If you add solutes, its boiling point increases. What else here? How do you know? Another thing. So then you have to think, okay, what other factors affect the boiling point? Well, a boiling point, I asserted in my lecture video, which I'm going to yet again recommend people watch, on boiling point and vapor pressure, their relationship. Boiling point is defined as the temperature when the vapor pressure of a solute is equal to the external pressure. So, point being that the boiling point is dependent on the external pressure. It depends upon what the atmospheric pressure is. Water boils at a lower temperature at high altitudes, and it boils at a higher temperature at low altitudes. So yeah, if you go up to, oh goodness, I should look this up exactly, but like if you go up to Colorado, water boils at, like, I'm making up a number, 95 degrees Celsius instead of 100 degrees Celsius. And that's because the external pressure is lower because you're at a higher altitude. So it depends upon some external factors, and it's also dependent upon any solutes being dissolved. How do you know when a compound's solution has dipole-dipole, ionic, or H bonding? So I'll talk about the last two. You know if it has that it has ionic bonding if it's an ionic compound. So you can usually identify an ionic compound as something that contains a metal and a nonmetal. If it has a metal and a nonmetal, it's almost invariably an ionic compound because metals have very low electronegativities. They don't hold on to their electrons. Nonmetals are highly electronegative. They'll grab electrons from the metal. So the electrons get transferred over, and you end up with a positively charged metal and a negatively charged nonmetal. Those are your two ions. That's an ionic compound. So you can recognize ionic compounds pretty quickly just based upon the fact that it contains metals and nonmetals. There are exceptions to that. There are such things as polyatomic ions. So something like this. This has only nonmetals in it, but this is actually an ionic compound because there is one ion and there's the other ion. This is ammonium, which has a positive charge, and this is the nitrate ion. That's the ammonium ion, that's the nitrate ion. Those are examples of polyatomic ions. They are little molecules that have ions, they have net charges, and since you have two separate ions, that's an ionic compound. And those also tend to dissociate into separate ions in solution. How can you recognize when something has hydrogen bonding? That is also usually can be easy to spot. Hydrogen bonding occurs whenever a molecule has any of the types of bonds I'll list here. If it has an oxygen-hydrogen bond, that's capable of hydrogen bonding. So I showed you a bunch of alcohols in your previous problem set. Those all are capable of hydrogen bonding. As the chain got longer, they became more characterized by London dispersion forces, but they're all capable of doing a little bit of hydrogen bonding through the alcohol group, the OH group. Something that has nitrogen-hydrogen bonds, these guys are also capable of doing hydrogen bonding. Let me specify. Hydrogen bonding is a type of intermolecular interaction. It's a type of intermolecular force. Just because something has hydrogens bound to it doesn't mean that it's capable of hydrogen bonding. Hydrogen bonding is not chemical bonding. It's not within a molecule. It's between molecules. And that interaction between molecules will only occur if it happens to have this type of bonding pattern, or this type of bonding pattern, or a fluorine hydrogen bond, and that's almost invariably, every example you're ever going to see of something that does hydrogen bonding is going to be hydrogen-oxygen bond. You will occasionally see nitrogen-hydrogen bonding, nitrogen-hydrogen compounds that are capable of hydrogen bonding, but they're less frequent, I would say, on average, than compounds that contain oxygen. And there's no more bonds you can make here. Fluorine only makes one bond to hydrogen, so this is the only compound you can make between hydrogen and fluorine. But basically, hydrogen bonding is a type of intermolecular force that occurs when you have a very, very strong local dipole, because this molecule, I think this one is working, this one has a very strong dipole pointing towards the oxygen. This has a very strong dipole pointing toward the nitrogen, because oxygen and nitrogen are highly electronegative. Same with fluorine. Fluorine being the most electronegative, so you get these very large dipoles. And nitrogen is capable of making 2 more bonds, so you can make some actual compounds with that. So that's a hallmark, I guess, to decide whether a compound is capable of doing hydrogen bonding. Now, whether it has dipole-dipole interactions, that's trickier. To predict whether something has a dipole, you need to know something about its actual molecular structure. You need to decide, okay, does it have these polar bonds, and do those polar bonds not cancel each other out? So to look up that, I'll give you a quick example. I did this in a previous video, but I'll run through it again. Something like carbon dioxide has polar bonds, but it is not polar, so it has a dipole that points that way towards the oxygen from the carbon, and there's another one that points towards the other oxygen. This one is not polar because those dipoles cancel each other out. They point in opposite directions. I'm pulling electrons to this side just as much as I'm pulling electrons to this side, so there's a net even distribution of electrical charge through this molecule, and it doesn't have a net dipole. A dipole is just an uneven distribution of charge. If you have more electrons on one side of the molecule than on the other side of the molecule, that creates a dipole. Now, a different example of something that has polar bonds would be something like oxygen and hydrogen for water. In this case, this is not a linear molecule, it's a bent molecule. And as a result, you do have dipoles towards the oxygen. Since oxygen is more electronegative, those dipoles don't point in opposite directions, they don't cancel each other out. I get a net shift of electron density towards the oxygen, and I have a net positive distribution of electrical charge on near the hydrogens. That creates a dipole. So yeah, predicting dipoles is quite a bit trickier because you need to be good at doing Lewis structures and VSEPR shapes to predict the shape of the molecule, and you also need to be able to predict relative bond polarities. Okay. If you want more practice on that, please check chapter 11 or section 11.2 in your textbook, or better yet, come to see me during office hours, or just any time during the day. I'm usually here until 5, and I'll be happy to help get you some practice with that. Are colligative properties Raoult's law? What's the application of Raoult's law? I would not say that Raoult's law is a colligative property. I would not say colligative properties are Raoult's law. I would say that Raoult's law is an example of a colligative property. in action. A colligative property is any property of solutions that depends only on the collective number of solutes dissolved in the solution, and not on the identity of those solutes. So Raoult's law says that the pressure that a solvent, the vapor pressure of a solvent that it exerts on the surroundings is related to the mole fraction of that solute times the vapor pressure of that, no, that should say solvent, not solute. Times the vapor pressure of that solvent when it is pure. So this is called Raoult's law. And what is the application of Raoult's law? It has a few applications or times when you can utilize it as part of analysis. Generally speaking, it is just a general observation. That's what a chemical law, or sorry, a scientific law is. It is a general observation that we've noticed over and over and over again, and it gives us a foundation to think about how do substances behave. Okay, if I take a pure solvent and I add in solutes so that its mole fraction is no longer equal to 1, then the effective, or the actual, or the resulting vapor pressure of that solvent is equal to its original vapor pressure times its mole fraction in that solution. That is the observation. Generally, that it ends up being reduced, and the amount that it's reduced by is dependent upon its mole fraction. That's Raoult's law. So this in of itself, I would say, is probably wouldn't be called a colligative property. I would not call Raoult's law a colligative property of solutions. What I would say is vapor pressure lowering, the fact that the vapor pressure of a solvent changes, the amount that it changes by is dependent upon the concentration of solutes, and that is actually the solute this time, times the vapor pressure of the pure solvent. So this is a property of solutions which we call vapor pressure lowering. And again, it only depends upon the mole fraction, the concentration of solutes, not necessarily what those solutes are. That's why we classify it as a colligative property. It's only determined by the number of solutes, the amount of the solutes, not their identity. So other examples of colligative properties are boiling points, freezing points. Those are colligative properties, and the amount that they increase and decrease by, those are called colligative properties. I mean, they're the same thing. If you're talking about the boiling point, that's a colligative property, and the amount that it changes by is related to it. So those are both collectively called colligative properties. There's another colligative property which I would love to talk about, and I am going to talk about because it's important. It's an important process, especially in the biological sciences. However, I'm feeling a little bit of pressure to continue on with material, so I'm going to sort of come back to this topic a little bit later, which is osmotic pressure, which is a tendency of water to move from areas of low concentration to high concentration. Yeah, I got that right. That's osmotic pressure. We'll talk about osmotic pressure at a later date. But that is also a colligative property. So case in point, if you take a red blood cell, or you take a red blood cell and you drop it in salt water, there's a low concentration of, maybe not a red blood cell. You take any cell, which usually has, I think it's cytoplasm inside of it, so it's mostly the cell is it's primarily composed of water, has a lot of water in it. You take that and you put it in a pure water solution, or a pure water solvent, water will tend to flow into the cell and lyse the cell. So the tendency of water to move in exerts a pressure on the cell. We call that pressure osmotic pressure. So that's osmotic pressure is also a colligative property. It only depends upon the concentration of solutes inside of the cell. not on the identity of those solutes. And if you change the surrounding liquid, you change it from water to salt water or from water to sugar water, again, it will only depend upon the concentration of those solutes and not on their identity. Why is the identity of a solute not important? Very much so. I argue it goes right back to this assertion right here. At least for things like boiling point elevation, vapor pressure lowering, it's the fact that the amount that it's lowered by is only related to a mole fraction. A mole fraction is just a number fraction. Number of this solute divided by the total number of substances in moles of substances in the solution. So the example I gave today was I just said solutes then. Let me come up with an example here. Mole fraction, let's say I had two solutions. One of them was, let's say this is, we're doing an aqueous solution, so they're all the solvent here is water. So the mole fraction, I could have 1 mole fraction of water in a sugar-based solution. So mole plus moles of sugar, so I'll say it's glucose. So just having a certain moles of glucose. Or the mole fraction or the solution could be an ethanol solution. So both of these represent the mole fraction of water in this solution. And remember, mole fraction is always moles of one substance. You can usually talk about the moles of the solute, but you can talk about the moles of any substance. So I'll just say moles 1 of one of the components in the mixture divided by the total number of moles. So a case in point here is that the factor that comes into play here is that it's a vapor. The vapor pressure lower. The vapor pressure is lowered as a result of the mole fraction of the water, and it could be lowered by its mole fraction could be lowered by the presence of any solute. No matter what the presence of, no matter what the identity of that solute is, you add in more substances, and the mole fraction of the water drops, just because the other solutes are increasing the total number of moles, so the mole fraction drops. And again, I prefer this as a potential explanation. It's just that the vapor pressure is due to the evaporation of the solvent, in this case, water. If you have other solutes, other substances which get in the way of that evaporation process, then the vapor pressure gets reduced. Doesn't matter what they are, they still obstruct that vaporization process. Why is it mole fraction of solvent and not solute for Raoult's law? Again, I kind of think about it this way. The Raoult's law is telling you how the vapor pressure of the solvent changes. It specifically talks about the vapor pressure of the solvent. And if we think about the vapor pressure of the solvent as being due to the amount of solvent available to vaporize, if you reduce the amount of solvent available to vaporize, then the mole fractions, or then the vapor pressure should be reduced. And the amount the amount of solvent available, the fraction that it's reduced by, that's going to be its mole fraction. So it might, instead of being 100% water, it might only be 90% water. So I expect the vapor pressure to be 10% lower, 90% of what it was before. That's going to be given by the fraction of water that's still available to vaporize. So that's why it's the solvent's mole fraction and not the solute. And again, I go back to this particular picture to sort of justify that assertion. Why is the Van 't Hoff factor of HCl 1 and not 2, since it has 2 atoms? Why is sugar's Van 't Hoff factor 1 and not 24? Okay, great chance for me to clear up a misconception. So HCl, first of all, so here, these are going to be the Van 't Hoff factors. HCl, your comment is why is it 1 and not 2? I went back and checked my PowerPoint. I do have it listed as 2 for the Van't Hoff factor, but it's not 2 because there are 2 atoms. It's 2 because HCl splits into H plus and chloride minus. Technically, it donates that hydrogen to a water molecule, but the point is it splits into 2 parts. You get 2 solutes for the price of 1, so to speak. So it should be 2. It's not just that because there's 2 atoms there. So case in point, you say why then is sugar C6H12O6, why does that have a Van't Hoff factor of 1? That's because this is not an ionic compound. It's a molecular compound. All of those carbon, hydrogens, and oxygens are all molecularly, chemically bound to each other. When sugar dissolves in water, each of the sugar molecules stays intact. They don't separate into separate atoms or separate ions. It's a molecular compound. So ethanol does that. I'm trying to think of other chemical compounds. So that's glucose, sucrose, fructose. I'm thinking of lots of sugars. Any oils, those are all molecular compounds. They're not going to dissociate in water, or rather, they're not going to. They will not disassociate in water. So that's the key thing there. It has a Van't Hoff factor of 1 because when you dissolve it, it stays as one whole molecule. It stays as one solute particle. It doesn't separate into 24 atoms. Why did the solution get colder during the demonstration? So yeah, good question. That's because the heat of solvation for sodium chloride is positive. It's an endothermic process. So first thing that happens anytime you dissolve salt, table salt, in water, sodium chloride has a endothermic heat of solution. So it draws heat from the surroundings. In this case, the surroundings for the sodium chloride is the surrounding water. So the water itself tends to cool down, meaning the entire solution cools down. And again, that's different for different solutes. Lithium chloride has a negative heat of solvation, so it's exothermic. Ammonium nitrate, I think, has a negative heat of solution. You dissolve those in, and the temperature will heat up, but the freezing point will get lower. So initially it heats up, and then if you try cooling it down afterwards, the freezing point of that solution would still be less than 0 in water. But the question of why did that particular solution get colder, it got colder because the solvation process is endothermic for sodium chloride. So there's 2 factors there to actually illustrate in that one example that I did. One is just that the solution got colder, and that's we kind of already saw with the first demonstration I did in the first week. The more important thing to point out is not only did the solution get colder, the solution dropped below the freezing point of pure water. And that was an illustration of freezing point depression. Its then freezing point has to be significantly lower. It has to be closer to negative 1 or 1.3. I didn't calculate the molality. Okay, could you please announce quizzes in class? Yeah, I will do that. I apologize. I was rushing through the end of lecture on Friday, and I slipped my mind. I apologize for that. I will continue to send out emails about quizzes in addition to announcing them in class. I will definitely start announcing them in class. I personally know, I understand, emails get lost in the shuffle of day-to-day life. I feel bad because I feel like I'm about to lecture people here. But that being said, I will be making frequently course announcements. So my options are either announcements either about materials and homework being posted, lecture videos, feedback videos being posted, so on and so forth. So my options are either send out an email to people or post an announcement on Brightspace. And I've heard through the grapevine of students that they almost never check those announcements anyway. So I figured people would be slightly more likely to notice a message from me if I sent it via email. So I guess I would just hope that people will continue to be vigilant with their emails, but that's no excuse. I should have addressed your. I should have announced the quiz explicitly in class, and I will try to do that in the future more so. Okay, that's all of your feedback questions for today. I will see everybody on Wednesday. Have a good day.